Hey there, I'm Ben Wickens, and I'm here with Kyle Helzer and Dylan Richards, and we are here to show you our first project for Physics 213. I hope you enjoy. All right, now here I'll run you through the introduction to the problem and kind of where we're going to start, our building blocks per se. Now, for this problem that we chose the charge strip problem, and this is one where you have a charge strip centered about the origin, and you have to find the electric potential and the electric field that is generated by it. So, if it's centered around the origin, it also tells us that it is 2L in the y direction and very long in the x direction. So, we don't really have a number for the x value, but we know that it is if it's centered around the origin, then it's going to go from negative L to L in the y direction. So I made a physical representation of this. If you look at the right side of the screen, you'll see the topmost graph has just a basic image of the density and what our limits are. So we got negative L to L. As you can see, it's centered about the origin. Now, if we look at the bottom graph, that will also be telling us that. But it is also showing us where our dy and y values are. So our dy is an infinitesimally small strip of this charge thing, and what that is going to allow us to do is solve for the electric potential and field about that point. Now, to solve for this, we will be using the chop, add, multiply method. And with this one, we are given this equation: e equals the integral of dE equals the integral of k lambda x dx over r squared times r hat. Now, what this is telling us is we are going to be integrating our charge density equation over the distance squared that we are measuring it from times the unit vector towards our little point. Now, we know that our lambda x is our charge density. So we have that right above our graph right there. So we're going to be integrating that from our limits of negative L to L. And we do that because the object has a uniform charge density. So it doesn't really matter where you integrate from. As long as you're integrating the entire thing, you'll get the right number. All right, now I'm going to run you through the assumptions that we made for this problem. So, one of these assumptions is that there are no external sources of energy in this problem. So that means that our system is unaffected from any outside sources, and the only forces acting on our system are our electrical field and the potential from the charge strip. So that means that this will be simpler to solve for, and we won't have to account for any outside forces or factors. So it's just the problem that we're working on, which is always a nice assumption to make. Now, we are also going to be using a point to find this, and we can use Coulomb's law, actually, because Coulomb's law is a way that we can find the electric field created by a point charge, and that is given by the equation that you see on the lower part of the screen, which is that the electric field of a point charge is equal to k times the electric potential of the point charge divided by r squared times r hat. This equation uses the distance of the point charge from the place of the measurement and the magnitude of the electric field to find the electric potential at the specific point charge. We can use this here because we're treating the point at which we are measuring like it's the charged point itself, and from there we can find the values of the electric potential and the electric field, and it'll make it for a much simpler solving process. So we're also going to assume that this point in space will be z distance away from our strip. And it looks like we're doing it from the top. So from the origin to z is going to be our distance. So that's going to be what we put for r, in case you see that.
I'm Kyle, and for the calculations of this problem, we started with our standard chop, multiply, add strategy to approach getting a value of the electric field at some arbitrary point in space. We first recognized the relationship between a small piece of charge dq and our charge density, which was given in the problem. We then related and put dq in terms of our charge density lambda and dy. We then multiplied our small piece dq to find the electric field created by that small piece dE. We were able to accomplish this with the use of Coulomb's law, a principle that we assumed would be applicable here, that being our dE is equal to k dq over r. Using our knowledge of what our constant k was equivalent to, according to the geometry of a thin strip and our knowledge of the distance r from the point to the strip being equivalent to variable distances z minus y. We then finally were able to add all of the small electric fields to find the electric field across the whole strip by integrating our dE across our bounds of integration, in which we determined by our physical representation of the problem, from negative L to L. Using an online calculator, we were able to simplify this integral in terms of established variables such as our density sigma, epsilon naught, and our distances L and Z in the y-hat direction. We were then able to find our potential V, which is what the problem asked for, by using our knowledge of the relationship between the electric field and the electric potential difference. We accomplished this by taking the integral of our previously determined electric field and integrating from our initial position Ri to our final position Rf with respect to z, which we changed the integral to zi to zf of E dot dz. We know that when taking this integral, our z hat and our y hat should cancel, as the dot product of these two vectors should result in a scalar, which is what we expect, as our potential value should be a scalar. We were able to use an online calculator again to simplify our integral into an uglier expression representing our electric potential.
Now that we have our answers, I'll be taking us through some sense-making techniques to double-check our work. First, I start off by confirming we have the correct units. While looking at our equation, it's important to note that the units for epsilon naught are farads per meter, the units for farads are coulombs per volts, and the units for sigma naught are coulombs per meter squared. Using this, I created a massive stack of fractions in the left of the red box. This shows the units of the constant. It's coulombs per meter squared divided by meters times farads per meter. If you look at the solution of potential on the right side, you can see the integral. We decided that the units for this are meters squared because all the units inside are units of length. In the middle of the red box, I made all the fractions side to side so we can easily cancel them out. And when you take a look at that, you can see that meters cancel out, and so do meters squared, leaving us with coulombs per farads. When we change farads to coulombs per volt, we can cancel out the coulombs, and we're just left with volts, which gives us the answer, which is just volts. Volts are equal to volts. The next type of sense making I'm choosing to do is covariational reasoning. By changing our variables, we can see how the results change. In this slide, I plugged in some pictures of some inputs we put in on Desmos. I excluded the constants at the beginning of the equation because I copied this solution straight from the integral calculator online that we used. However, we'll still see the important general trends even without the constants. After changing the values of L and Z, we found that the Z value must be greater than the L value. This is because of the natural log in the equation. There's a Z minus L in the denominator. So if L is greater than Z, then there will be a 0 in the denominator, and the equation will be undefined. As you can see on the equation on the bottom, we did that and it says undefined. This makes sense because the point 0 we're looking at is supposed to be outside of the thin strip of the length L. So if the Z is less than L, then it'll be on the strip, which won't work. We found out when Z is greater than L, that as the Z value increases, it becomes more and more negative, and the potential energy decreases. This inverse relationship makes sense because as the distance Z increases, the point is further from the strip and therefore less affected by the electric field, which is negatively affected by distance. Okay, for our reflection, we'll be comparing the problem we just solved to problems we've previously solved in Physics 213. This problem is similar to the activity 3-2A from the week 3 studio and the activity 1 from the class's homework set 5. In activity 3-2A, we had to find the electric field at a point on the y-axis of a wire given its dimensions and non-uniform charge density. In our problem, we were also given the dimensions of the charge shape, its non-uniform charge density, and we were asked to find the electric field on the y-axis. We chose to refer to the distance of the point as point Z, but it's still the same dimension. So The only step in our problem that isn't in this problem is converting the electric field to electric potential. Here's a picture of the notes that demonstrate how to solve activity 3.2a. I circled some of the parts that show the chop, multiply, and add strategy in use. We use the same technique in order to solve our problem. To the right, I underlined the solution for the electric field, which looks very similar to our solution for the electric field. In their solution, though, they didn't factor in k, but if they did, it would give them the same constant that we had. The only difference is the right side, which is the result of the integral, which is different because we had a different shape. In activity 1 of the week 5 homework, we take a look at a problem that asked us to create an equipotential graph based off of an electric field vector map and to find the electric field at every point. This is a picture of the solution that was posted for activity 1 on homework 5. Although there's just a lot more steps going on that aren't really related to our problem, I highlighted the areas that show the formulas that equate the electric field to the potential area. The lower box shows this equation, and the upper box shows the final solution. We use the same equation, E is equal to negative potential, to convert our electric field that was previously calculated into our final answer of the potential energy.